Hello, my name is David Criado. I'm the CEO of Radian, and today I'm presenting you our thermal analysis software. Radian is a standalone thermal analysis tool that runs in the cloud and is accessed via a web browser. As you can see, I'm currently using Google Chrome, and if I type the URL app.radian.systems or click login in our website, I end up in this login screen. I need to input my email and my password as my user credentials to enter the application. So the home view of the application is the projects view. The projects view gathers a list of your projects, where each project is supposed to store a collection of models, scenarios, and thermal solutions that belong to a real-life project of your organization. On the left side of the screen, we have the navigation bar. So we have the home button that drives you to this view, a list of your projects that you can quickly access from here, and the data bank, which is a catalog of entities that you can reuse across as many models and scenarios as you want. The data bank can also store parts, materials, surfaces, orbits, attitude models, attitude files with quaternions that you can upload as well. And we also provide you with some public entities that you can use since the start of your models and scenarios. And finally, we have a link here to the support center with some documentation that is useful to use the tool. And finally, also some user settings and other actions as well. If I click on this project here, I dive into the project view. This view is divided into two areas. The upper part is devoted to the uploaded CAD files that we converted then into thermal models. And then the lower part, which comprises the thermal analysis process that we have sequenced into models, scenarios, and analysis cases. The models are a thermal representation of your satellite or subsystem and gather geometries, contacts, and loads. The scenarios can be either orbital or enclosure. The orbital recreate the space environment, and the enclosures have custom boundary conditions of temperature and heat. Finally, we have the thermal solution, which can be either transient, periodic, or steady state. Having a quick look at the CAD file, we can see an intermediate step where the CAD file shapes are converted into valid geometries for the thermal model. In this example, we can see some valid geometries which are recognized by Radian, and some invalid geometries which are not and need to be modified. Our modifications so far include removal of curved shapes like drill holes and rounded corners, replacement of geometries by their most similar shapes, and optimization of thickness for thin solids that have a negligible thickness. And once all the necessary geometries have been validated, you can apply properties to them and generate the thermal model. So going back to the project view, we can now enter the model editor to see how to create a thermal model. So the model editor consists of two parts, the model tree and the model viewer. The model tree has parts that are comprised by geometries, contacts that can either be detected by proximity or created as custom values, and heat loads grouped in different load states. These load states can then be selected in the scenario as events to compose the desired operational mode. If I click on one geometry, a panel appears in the right side, let's see, with the properties of the geometry. So then I can tweak the material, the position, the orientation, the dimensions, and so forth. I can also set a surface treatment for each of the faces. If it's a shell, it will have two faces, but if it's a solid, it will just have one. And finally, I can tweak also the mesh parameters with the number of nodes along each dimension and also the proportions of the mesh. So moving on to the orbital scenario view, we can see now two new sections. So we have the load events to the left, bottom side of the screen, and the mission parameters to the right side. The load events can either be defined as perpetual, to be active during the entire scenario, a custom, which will be active only during the specific segment that you can define, and finally periodic, that recreates the duty cycle of a cyclic dissipation. Regarding the mission parameters, we can define the orbit, the attitude configuration, and the time parameters. The orbit, let me open that for you. The orbit can be created around any body in the solar system, using the classical orbital element or the local time in the case of an SSO. The attitude configuration is built based on a sequence of orientations. And each orientation can either be an attitude model or an attitude file in CSV format with quaternions that you can upload to the software. And finally, we have the time parameters. That is the real-time epoch of the simulation, the duration of the scenario, and the step at which we probe for external heat fluxes. Finally, for each of these stages, we have two tabs, the editing tab and the results tab. So the editing tab is what we have seen so far. It's the model editor and the scenario editor, and also the case editor with the thermal solution parameters. And the results tab is comprised by the results up to the stage at which you're at. So if you go to the results tab at the model view, you will have the model results. If you go to the scenario, you will have the model and the scenario results. And in here, I want to present you the whole thing, which is not only the model and the scenario results, but also the thermal solution results. So for the thermal model results, we have some quick stats with the number of nodes, the total mass, total capacitance. We are also able to generate some summary views with the mass budget, capacitance budget, bill of materials, bill of surfaces, and we can also compute the conductive couplings and the radiative couplings between the nodes of the thermal model. For the scenario view, we are able to recreate the orbital environment and get the coordinates, the eclipse moments, the orientations, and the irradiances as well. And we're also able to generate the heat fluxes. The heat fluxes in an orbital environment are provided by the sun, the planet, and the albedo. And we are able to get not only direct heat fluxes, but it also absorbs heat fluxes as well. Finally, for the thermal results, we get temperatures and heat inputs. We have the total heat, both in and out of each node. We also have the couplings heat inputs, either by conduction or radiation. We have the environmental heat inputs provided by the solar, planetary, and albedo absorbed heat fluxes, and we also have the dissipations. Now, we have three ways in which we can represent all of this information. We can view the results in a 3D view with a color map. We can plot it in an XY chart, or we can download it in CSV format. Every result that is plotted here can be downloaded. So for instance, I can check the temperatures in the model view and see the colors that correspond to each of the temperatures at each given moment, both in eclipse and in sunlit. And I can hide different geometries to disclose and reveal the temperatures at the inner part of the satellite. I can also plot these temperatures in an XY chart. And now we can see a nodal distribution of the temperatures, but I can aggregate those temperatures by part. So they appear grouped with a maximum, average, and minimum value. And if that's not enough, I can also group them by time. So I can just see what's the maximum and minimum temperature for each of the parts for each of the simulations. So in here, we will have the predicted temperature ranges. Finally, to show you the last way in which we can present our results, let's see, for instance, the planetary mission heat fluxes. And you will see now the results plotted in the mission environment view. All of these views can be enlarged and seen as full screen, both the mission model and also the XY charts. And that is all. Thank you for watching this video, and please feel free to contact us for more information.